Thank you very much for the introduction, and thank you very much for asking me to talk. Service-oriented architectures and the results from Arrowhead and its usage in the EMC Squared project. But also call it Building Automation System from Internet of Things, since that's from where the Arrowhead project is coming. Let me give you an example of what's going on. This is a picture from Poland, from KGHM, the third largest copper producer on the globe. They are using conveyors to actually transport goods. And we made an analysis of a number of components and systems used in a mine. And where do we want to do automation? Where do we want to put sensors, actuators, get the information from? And we started to analyze conveyors. There is, of course, a few more things, quite a lot more things in a mine. And broke that down into bits and pieces and came down to the idlers. These are those ones, rollers, which are rotating and on which a rubber belt is put. These are expected to revolve. If they don't, they're going to cut up that rubber belt in minutes. And this is a thing you don't want to happen. Since if that happens, you have a longer maintenance situation to care of. It's quite interesting to then analyze just one company. This KGHM, they actually have 120 kilometers of these conveyors. For every major, there is 3 of these idlers. In every idler, there are 2 bearings, which are responsible for that idler to actually revolve. If we summarize that, we come to something like 720,000 bearings, which we actually want to monitor. And that's just one company. It's an interesting number. We'll keep that in mind for the rest of my talk. But it's an interesting number. Cisco have been talking about these multi-billion things, and based on the previous slide, you can see, yes, this is probably not true. The figures are too low. But the interesting thing is that to build massive automation system with current technologies is probably not possible at all. Basically, since we don't have engineers enough to do that. So we need to move from an engineer-driven development to something where machines or a kind of autonomous way of connecting things together into the future. And this is one of the great challenges where Arrowhead is putting its emphasis. And I just gave you those figures. 68 million euros, 78 partners. The web page is there, arrowhead.eu. There is quite a bit of information around there. So one of the things we are really looking for is to take automation systems. This is the ISO 95 standard of how to represent an automation system. We want to, this is what people sell today, ABB, Siemens, Schneider, etc., etc. With proprietary technology at certain levels here. We want to move this into a cloud situation, using Internet of Things, system technologies, and kind of ideas that Corbett was talking about earlier on today. The approach we are taking is saying, okay, things are connected to the Internet. We can talk to them using the general protocols there. We need to build system of systems. The approach that we have selected is service-oriented architecture to do that, meaning abstracting devices to services, and basically we don't care. We say that, okay, we can deal with what's going on the hardware level. But to abstract things to services and say, that's where we have the possibility to connect a bearing to another system, or hundreds of thousands of bearings together. So some basics about service-oriented architecture. the services are produced by a service producer, let's say System A, and it's consumed by another system. So it's basically about the exchange of information or data in between two systems. There are some key properties around this. One is what people refer to as loosely coupled. Each of these systems are on their own. They are autonomous. They are distributed. They are not for sure in the same location. That can be. The owner of the system is actually owning the data the system producing. There is probably not any global God telling that these things are going to exchange data one way or another. Might be, but it's, in most cases there probably is not. We are talking about late binding. Who is talking to who? That's a question what happens in runtime. Professor Corbett was touching on that in his talk as well. This is not a design type situation. Things happens now. And that's determined in runtime and based on what's going on in the total system. To be able to utilize these services, there need to be ways to actually find them. One way or another, publish them and to register them or make them visible, made endpoints, made the services visible. And that's one side from a producer to say, I'm here, I can give you something. And from a consumer side, you need to be able to discover, say, okay, can I find a pressure sensing or a power meter on a ship or whatever? Can I get that information? So these are key properties which we need to actually build these type of systems. From an arrowhead point of view, we have taken a few basic standpoints. So we are very much talking about information-centric. So it's the information or the data that we are talking about. And the assurance about the integrity of that data and who is allowed to actually consume certain information is at the level of the service exchange, the exchange of the information. That's when we decide that. So it's decide runtime based in real time. Most of the situation is that it's publish and subscribe. So you say, okay, I'm here, someone can subscribe to your information. Either say I want it every 10 milliseconds, or I want it just when pressure is higher than something, or temperature is higher than something, or energy usage is higher than something, or in a window of certain interest, so on. Which means that data most often is pushed to someone when on a certain event. You can even design this system to do pull, which is the traditional way of doing so. I'm reading data every 20 milliseconds. To build these type of systems, there is a minimal number of kind of core things you need to actually do that. So try to say what is the minimal mandatory services to build a system of systems. To make that as lean as possible. So these are the underlying things we are using to go from there to there. How are people doing this today? We see that people say, okay, yes, we can build clouds. Microsoft, IBM, Google, etc. say, yes, we can take care of all your data, we can do some computation, and it's done somewhere around the globe. We have one of Facebook data centers in just kilometers away from the university. It's huge. It's actually 3 big halls, of each of them something like 6 football fields, something like that. It's enormous. And then looking at the power supply to things, it's quite interesting. Okay, that may be a way of doing it. there are some interesting reviews on how to compare these approaches. There was a paper published at ESFA a couple of weeks ago looking at a number of these and what are the differences. It's interesting to see that each of these approaches that's now being published as main offerings and so on, they are driven by one or two applications. So still rather specific, but still that's the way what's going on. Arrowhead is taking a little different approach. Yes, talking about automation. And automation is most often physically very local. The control loop is local. The control of the temperature in this room is based on sensors in this room, and there are ventilation control that's very local, physically local. Maybe the fans are, they're probably on top of the roof here, but the valves, they are here in this room. That enables us to make what we call local clouds. Very different from what people are talking about fog. Instead of cloud, people are talking about fog, but that's having the internet all the way out to any sensor. With local clouds where we put a boundary around that. And that enables us to say, okay, within that cloud we can have some understanding of real time. We can, for example, use TTTech technology within a certain cloud and say, okay, yes, we can handle real time in that certain cloud. We probably have some better ways of handling security. There are fewer players in that local cloud, and we can do things regarding security maybe in a better way than having the whole internet at the same time connected. And regarding engineering of these type of automation systems, we have much fewer components to actually consider in our engineering, in particular when we come to safety, security, and also to just physical functionalities. So from that point of view, we argue that local clouds are an interesting approach to do this. We can have clearly better control of latency. Of course, we understand which things that's in there, security, engineering. But we also understand that we need to have inter-cloud communication. And it's pretty clear that even within the same cloud, it's not sure that you do have the same technologies on every device, every system that you put in there. There might be different hardware communication, might be numerous different service-oriented protocols. There's a place about 10 that's widely used. So there need to be some translations. If we look at classical automation systems, they are, even if they are called distributed control systems, they are quite centralized. They are pool-based, they are hardware time, and in particular they are design time binding. So every link that we have, they are determined at design time. But it's interesting to see that there seems to be an upper bound on how many devices you actually can connect to these type of systems. We take an example of the largest, one of the largest installations I know about. It's was an installation of an ABB 800XA system up in Kiruna, one of them in the iron ore mines there. They had some 10 to the 5 I/O points. And this is a few years ago, and that was at that time the largest installation ever ABB had delivered. We're talking about a couple of 100,000 interface points, which this type of system is doing today. We are not talking about 720,000 interface points just for bearings in conveyors at one company. It's already there, starting to be an order of magnitude of difference. And if you then consider, for example, a building like Heathrow Terminal 5, in that building there is already 5 million connected points, but probably in something like at least a couple of hundred different separate systems. So it's yeah, coming back to one of my slides, why we need to go from engineer time, design time bindings to real-time bindings and machines doing it. Cloud-based automation systems. You have a choice of centralized and distributed control, either push-on-event or pull-based thinking. It's late binding, it's runtime binding. A number of people will argue about, can we do this real time? But what I'm saying is that if we make local clouds, we can certainly build real-time stuff within those local clouds, where we have in between the clouds real-time. So for example, if you build things on a car or an airplane, as the examples that Andreas was showing earlier on, I'm pretty sure that we can make real-time plans there. If we then think about these IoT properties, which properties do they have? Things comes and goes, yes. They may live, they may not live, they may be available. Certainly they have limited bandwidth. They also may have limited power supply, energy supply. And it's pretty clear that the integration of Internet of Things systems have to be dynamic based on a number of these considerations. Based on the demand someone wants to need our information and whether it's available. So if we move to this approach, cloud integration of IoT devices will need to have some certain properties. And the way Arrowhead is doing so, okay, communication hardware, yes, there is tons of existing technology, use that. But we say also that we need to build support for making local clouds and to make that very simple. So for that purpose, Arrowhead is going to provide a number of core services which we call mandatory. If you have those, you can build a cloud and you can start to rather simple orchestrate a system of systems. In addition, Arrowhead provides a number of automation functionalities which is basically needed to build distributed control systems, SCADA systems, and so on in the cloud. And for the purpose of people using, for example, one supplier uses COLA protocols, another supplier uses MQTT protocols. Can these two talk to each other? We need some type of translation. In this way, we say, okay, we can build local clouds with a number of systems that's in there, provided that we have three fundamental things, what we call information infrastructure, system management, information assurance. These are classes, and the real fundamental stuff we need is a service registry, an authorization system, and an orchestration system. These are necessary to enable these two to actually talk to each other. You can then build interaction diagrams like this. I won't go into details on this, but this is the communication needed to actually get these two, system A and B, these two to actually talk to each other. They need the other three to actually establish that they are existent, that they are allowed to talk to each other, and who they're going to talk to each other, and on which regarding which routes they're going to talk to each other. Next, we can build a number of these clouds by allowing intercommunication between them. In certain clouds, we can certainly create closed loop control, real-time stuff. A cloud like this might be a car, but it also might be just around the engine of the car. And all the three clouds, this might be the entertainment system in a car, and so on. But this is back to the problem that Herman Koppel's was discussion. How do you divide your system? And that's going to be a much more important part in the future design of larger systems. Connected to EMC Square, where we say that we want to run multiple applications on one single machine, a multi-core machine. We can say, okay, well, one of these machines can have a service interface and then a number of services dependent on these applications, and then we solve something in here based on existing technology. Or the other approach is saying, okay, every system, let's say an ABS system, engine control, other systems, each of them are providing services on their own, and we actually build a cloud on a ship. Open question still, what is the most interesting way to go, but it's interesting to explore these two directions. Just a picture on how real time. What can we do in that local cloud? As I said, we can use some for example, TTTech. You can do that. Some people then argue that service-oriented architecture actually adds a lot of overhead in protocol. Yes, they do. There is some bit of work on how do we reduce that overhead, and the solution is compression. There is a protocol EXI, which is standardized since 2 years ago, something like that. And there are a couple of publications on that. This is one of my previous PhD students. It's quite interesting to see that his work was standardized before he published his thesis. So quite strong in that respect. This is basically not a problem today. And this can be addressed by selecting within a certain cloud. We select something where we can say, okay, yes, we can do real. So real-time is possible using local clouds. I don't think real-time is possible using global clouds. In addition to these mandatory service that Arrowhead is providing, Arrowhead also provides a number of other services. I won't go into any details on that. They are described and will be available. Most of them will also be available as code. Can we build automation systems in a cloud today? These are some necessary technologies listed. You can argue whether this is the right list or the wrong list. It's never mind. What I want to point out here is for each of these, we will today find either products on the markets or demonstrations in industrial environments, so on and so on. Meaning, the industry is moving towards enabling this. We are not far away from enabling this. There are actually companies already selling, offering to the market cloud solutions for certain parts of the ISO 95 pyramid. A lot of these things are going to be public from the Arrowhead project. We are right now generating a wiki that will be located here. It's not open yet, but very soon. There are going to be documentation, cookbooks on how to do the mandatory core systems. They're going to get executable images. They're going to be code. They're going to be tools for system management and tests and so on. They're going to be simple services and sample automation services with source code. And we are in the process of building this site right now. We will make this available as kind of pre-usage for a number of people in particularly work package 1 of EMC Square. And I've just tried to put one of our Volvo friends into there, and we're still struggling with some access rights stuff on things, but we are soon there to really provide you with tangible results from the Arrowhead project into the EMC Square project. this is the kind of the framework and the architecture of what the information is going to be available. Motivations, the technical architecture, core services and systems, how to implement the application system, examples of application services, documentation models, and test tools with compliance. If we compare this to the requirements from EMC Squared, what happens then? We've actually done that exercise in Work Package 1. And we have grouped a number of the requirements, or we're trying to group most of the requirements into things like authentication authorization systems, data encryption, security encryption systems, certificate distribution, etc., etc. In some places here you will see that Arrowhead is listed. That's where Arrowhead actually can provide solutions to working solutions to an architecture which will actually suit the EMC Squared requirements. And these requirements now is around information assurance. We've done the same thing around system management and the same thing around information infrastructure. And about 50% of the requirements can be supported by Arrowhead technology. And there we will have solutions. For the others, we will provide an architecture from the EMC Squared project, but no solutions. So, in conclusions, I think that provide platforms like where we have service, kind of a service platform out of these multi-core machines with multiple applications. It's extremely important that we can handle security and it's scalable and flexible. Meaning we can do things in runtime, we can handle things in runtime, things are not design time. We can provide latency guarantees in clouds. Now we can handle engineering, configuration and deployment dynamically. And maybe not for EMC Squared, but for, I think it's, what is DP11, IoT, the IoT part of EMC Squared. Scalability will become a very, very crucial point. I think that concludes my talk, so thank you very much for listening.